I'd like to start thanking the organizers for the invitation to speak here. I'm enjoying a lot this conference. There are plenty of very nice topics and lectures, and the weather is fantastic too. So this is joint work with Mario and Oscar, regular collaborators, and this time Samuel Tratwin from Zurich. Okay? And it was uploaded to the archive the same day as Brian Collier's paper. We agreed. And the plan of the talk is to start explaining some motivation and the objectives of the talk, and then these are like 4 moduli spaces. Actually, most of the results will be about the third and the fourth and the fifth part, so the coupled harmonic equations and Hitchin moduli space. But we will have something to say a bit about flat connections in each bundle. So we'll start with the motivation. So the motivation is kind of, well, if we have a compact oriented surface and a complex semi-simple Lie group, so these two will be fixed throughout the talk, sigma and G. Then, in particular, you have these homeomorphisms. So these two in the middle are moduli spaces of solutions to some equations. And these other two may be thought as more algebraic geometric moduli spaces. And so I will actually focus on these two. But we know that these correspondences depend on the choice of a complex structure J on the surface. So we have a picture like that. C could be maybe the Teichmüller space, and you have different moduli spaces that change with the complex structure that can be thought as like a background field. And from the point of view we have had in other moduli problems with Oscar and Mario, we would like to make this complex structure interact. I mean, in the same way that if you think of the flat connection or the field as particles that are on a field, which is like the gravity, we expect the complex structure to have some back reaction from these Higgs fields and connections. Okay, so our approach to universal moduli is this: some more, if you like, more physical point of view that they should interact, and this space should be curved by the interaction. Okay, this space of complex structures. So this is our viewpoint. Okay, how do we model this interaction? Is via symplectic geometry. We take the approach of Atiyah and Botts in their seminal paper on, the self-dual, the Young-Mills equations on a Riemann surface. And the idea is to plug this space of complex structures and actually see whether we can compute some moment maps. Actually, as in Brian's lectures, we will see that all we can get is some presymplectic quotients. I mean, it's not exactly what he does, but has a similar flavor, that there may be some degeneracy of the symplectic structure. Okay, so this is kind of the 4 universal moduli spaces we want to study, in which the complex structure is part of the data of the moduli. I want to, well, for younger people, let's say which are the more influential works in these. I mean, there are plenty of, there are many other ones, but maybe these are quite important for us historically. And I should also emphasize the role of for younger people again of this result of Narasimhan and Seshadri. That is kind of the origin of these Hitchin-Kobayashi correspondences. Okay, so don't forget this, and this was made here in India, and they produced an excellent school of algebraic geometry bundles. Does not work?
Can I ask a question?
Sure.
So in that picture, don't all those moduli spaces live over the same point in Teichmüller space? I mean, over each point?
I mean, in principle, they should fiber over the Teichmüller space.
Yeah.
But actually, the idea is that this Teichmüller space should be inside this moduli. But there will be a map to some Teichmüller space. But it should actually be part of the moduli, one of the fields. Okay?
But why are they over different points? I don't understand.
Because I can't
draw them all in one point. Yeah, okay.
But that's it. They should be everywhere. They should all be everywhere. Yeah. Sorry, maybe this is more confusing than helping. Okay. So as I said, yeah, this Narasimha and Seshadri made this school of bundles and moduli spaces and producing excellent mathematicians like Ramanujan here. And now, for more contemporary works, of course, I should mention that these may be related. We still have to understand. This is really, there are many open questions here, I think, but we expect this is complementary to the work of Brian with his collaborators and the work of Nigel that he explained 2 days ago. So we expect we are approaching the same problem from different angles. Let's see. And maybe, I mean, in algebraic geometry, you usually construct moduli spaces relative over some base. So it's not the same as what we are doing, but because we want actually this base to interact. But there is a lot of activity now in algebraic geometry on understanding these Higgs bundle moduli spaces over the moduli of curves when you are on a nodal curve, for instance. So this may be finally related to, I don't know. Okay, so this I want to speak a little bit about the origins too, because we are using as foundation for this work Marius' thesis, because the main techniques were developed there. And that was in 2009, and then finally we did more work and published the paper on this in 2013. And later we collaborated with Samuel Touchman when he was a student of Gilman Salomon. And actually one of the chapters of his thesis is called Universal Hitchin Moduli Spaces, like this talk. And there were some calculations already there. So we left this locked away in a drawer. And then Richard Wentworth came to Madrid and gave a series of lectures. And this revived our interest and took the calculations and kept working. And this is what I'm going to speak about, okay? So this is more personal, how this developed. Now, I want to give some notation that will be used throughout this talk. So as I said, G will be fixed, and K will be a maximal compact Lie subgroup. This is standard, and we kind of try to follow, not always, but Brian's notation. Okay, that will not be showing up so much, but this is just a Lie group anti-holomorphic involution. The fixed point is the maximal compact K. And we will also leave this by invariant inner product on the Lie algebra. And as I said, sigma will be fixed, and then we have a principal bundle there, and then reduction to the maximal compact subgroup K. Oh, thank you. Yeah, it will be E all the time. That's in my mind. And the main objects are these. No? J is the space of complex structures that we want to couple. G is the space of, if you like, G connections, or sometimes we call them complex connections. And A is the connections on EK, so we call them sometimes unitary connections. Okay? We have J and G. As usual in Higgs bundle theory, there are several ways of parameterizing complex connections. And one we will use a lot is as pairs given by unitary connection and a section of the adjoint bundle. Plus time, I mean, it should be symmetric, so we multiply by I. You can think of this. Yeah, sections, I mean, one forms, right? Okay, sorry. Okay. So we start with the first moduli, flat connections. So we will not have so much to say, but we'll say something about this case. So the first, I mean, maybe we should, from the start, I should start saying that what we want to study is this space times this, of course, that's clear from the beginning. And we want to study it as a vibration of the space of complex structures. So we call this X. Okay, and this talk may be thought as a talk about the geometry of this vibration. Now, let's see. I mean, we start as in Hitchin seminar paper with, and I mean, yeah, it's already there. You have a constant complex structure, J, and a constant homomorphic symplectic form, omega J, on the space of complex connections given by these two formulas, which don't depend on any complex structure on the Riemann surface. And there is a complex moment map for the canonical action of the complex K2 here, okay? And Nigel already calculated that the moment map, the vanishing of the moment map is flatness of the complex connection. Now, as usual, when you have a complex symplectic form, something like this. Yeah, somewhere. Some Z group. To write to compute the quotient, if G is complex, you can do it in two steps. No? You first reduce to the vanishing of this complex moment map, and then if you have some symplectic structure, real symplectic structure, I mean, or some line bundle with a linearization of G, then you can compute the quotient as a symplectic reduction by them. maximal compact group or as a GAT quotient. And then these two constructions should be equivalent by some Hitchin-Kobayashi correspondence or some Kempfner's theory. Okay, so we first take the GAT point of view and then restrict to reductive connections. That's stability in this case. And so the moduli is of flat connections can be thought as this quotient, not reductive flat connections modulo the action of some gauge, complex gauge group. Okay. So our first goal is to construct, make a relative version of this over the space of complex structures. And there is something we can new. I think we can say something new in this case. So since we have a constant complex structure, a constant holomorphic symplectic form, then we can just consider the diagonal complex structure on this space X, this new space, with some canonical complex structure that is on the space of, on the space of complex structures, which is given by this formula. That's called J. Okay. We have this canonical complex structure on X, which doesn't depend on any, it's constant. So as in classical papers, we can perform some symplectic reduction. But now, since we want interaction with the complex structure, we have to enlarge the gauge group. So we start with the identity component of the group of diffeomorphisms, and we want it to act on the space of complex structures, J. So what we do is make this new extended gauge group, which is given by automorphisms of the principal bundle that cover elements of this identity component of the diffeomorphism group of the surface. Okay, and this acts on X, on this space of complex structures times complex connections. And there is a map from this space to this one that just maps G to G check. Okay, and this is surjective, and its kernel is the complex gauge group given by transformations covering the identity. So we have this short exact sequence. Okay. We want to calculate a moment map for the action of these in the middle for this space. So we need some, in principle, symplectic structure. What we actually have is a complex Hailer fibration. So we see this over the fibration here, as I said. And okay, this is presymplectic anyway. The pullback of the constant complex symplectic form on G to X, and we calculate the moment map, and it's just given by the curvature. So again, the zeros are just the flat connections. So, the calculation is based on the methods of Mario's thesis, but this already means we can perform some. We can make the first step, as I said, and so we restrict to flat connections, that's like an integrability condition. And we propose, but we don't have a really deep reason to believe this, that anything else we need to calculate the GAT quotient is reductivity. I mean, there are reasons, but no theorems. We need some blind bundle, if you like, to explain why this should be true. Do we propose that the universal moduli space of flat connections is flat connections together with the complex structure? And at least we know that by the construction I just said, this has an induced complex symplectic, presymplectic structure, okay? And it fibers over, of course, by naturality, over the Teichmüller space. Okay, so this is the first moduli. Now, the second one will be, I think, more interesting. Got some equations here now. And this will need some ingredients that were not in various theses. The new ones are KLA vibrations. So they are vibrations like this that are holomorphic, and they have a fiber-wise symplectic structure, okay? This is a KLA form on the fibers. Here's the definition, okay? The formal definition. Now, there are two things I want to use. I mean, one problem is we can't perform, in principle, symplectic reduction if this is not closed, which isn't in general. It was in the other slides, but if this varies with J, then this can't in general be true. So Lerman and Sternberg introduced the notion of a coupling form, which is a closed real one-one form on the total space that restricts to the given fiber-wise KLA form on each fiber. And it defines an Ehresmann connection on this fiber bundle, given by that, and it's a scalar in some sense. Tau is parallel transport. And the last ingredient is that when you have this, and you are able to construct a coupling form, if J also has a scalar form, then you can combine them, okay, and construct some close to form on the total space of the vibration. That's called minimal coupling. And it depends on the choice of a parameter. Alpha. And well, it's known that if the base and the fiber are compact, then for a very small or not so, this should be 1, of course. For very small alpha, this is again scalar. We're not in that situation, but maybe we can still do something. And that's the idea. So this is called minimal coupling. And that's what we will, sorry, or yeah, minimal or weak, because alpha may be very small. So we apply it to this harmonic, to obtain these harmonic equations, but coupled to complex structures. So using the definitions I just said, we see that this space X is a Kähler fibration. The product, I mean, the complex structure is the one I said earlier. Okay. And we use Nigel, I mean, this is in Nigel's paper, maybe written. Yeah, this is, there is minus here because we are taking the Q joint. Yeah. Okay, so this I gives this minus. Are what? No? I mean, this is infinite dimensional. It won't be, in fact, and that will be a terrible problem. Yeah, that will be one of the problems we'll have. And we expect this is related to some problems of signature in Brian's lecture. Okay? But you are right. If this is not even finite dimensional, that will be crucial. Yeah. Thanks. Okay. So again, if we want to make this symplectic reduction construction, we need a total presymplectic or presymplectic reduction. We want the presymplectic form on the total space, and we apply these methods of Guillemin, Lerman, Sternberg. So we need a coupling form. That's what I am going to construct. And I think this is already in calculations by Nigel, right? Did you calculate the variation with respect to the complex section? No? So this is not really, I mean, this is just rephrasing something known. That you can construct a 1-1 form on the total space with this formula for this Kähler potential. And the point is that it restricts on the fibers to what I said. And it's closed. And well, it defines a Kähler connection by this. I mean, there is any Kähler fibration has a Kähler. If you add a coupling form, then you obtain a connection. And in this case, it's just given by this formula. So you see the curvature is non-vanishing. Maybe we can focus on this part anyway. We have a, oh, sorry. So this should be sigma, I guess, because we want it to be closed. Mm-hmm. So we have a coupling form on X that restricts to our given Kähler forms on the fibers. We have a canonical complex structure. And then we propose this presymplectic form on the total space, applying these weak coupling methods. But it will be, in general, degenerate, and actually always, in our case, non-definite. Okay, non-positive, non-negative. It's a mixed signature. So we propose this. And as I said, it depends on the choice of sign of alpha, or if you like, if you want to keep alpha positive, you can just multiply this first part by plus and minus and change the sign. We choose this convention. So in the case of -1, I mean, I don't know whether, I mean, we have two possibilities here. And in the -1 case, the symmetric tensor is non-degenerate. Okay? But it's a positive in the vertical direction and negative in the horizontal direction. Okay? That will create problems. And the +1 case, this changes. If you look at the line, it will change, and it may be degenerate. Okay? As I said, this creates problems. But anyway, we keep working and see what we can construct. So in this case, since we want coupling the complex structure to the rest, again, we want to enlarge the gauge group by these Hamiltonian symplectomorphisms. This is quite, I mean, this comes from Mario's thesis, this approach. So we consider this extended gauge group of automorphisms of the principal bundle that cover Hamiltonian symplectomorphisms on the base. Okay? And again, there is a map from the second to the first group. Everything, again, I should say, is infinite dimensional. And the kernel is the usual gauge group of transformations that cover the identity on the base. Good. So the usual theory deals with G and K. Now we want the extended version to act on this bigger space. And we can calculate the moment map for this first impractive form. And when we get this is a calculation. This extended gauge group, the unitary one, if you like, acts in a Hamiltonian way on this space. And the vanishing of the moment map is given by these two equations. Okay. And this is really, really kind of direct from Mario's thesis. So we also want to impose the other condition, the integrability condition I said earlier, corresponding to a complex symplectic form. So if we impose that, which means flatness, we saw that, the vanishing can be written in this way. These are the equations we get. So here we have a complex structure, J, the unitary connection, and the psi, and the section in one form, with values in their joint. Solving these equations, and SG is here the scalar curvature of the metric. And this appears from earlier work of Fujiki and Donaldson, and I think even earlier, Whelan knew this. In the case of surfaces, which is the one we want. Okay. So you see that there is some novelty here, this cubic term. And all we have said means we can construct a kind of universal moduli space parameterizing complex structures, unitary and complex connections, parameterized this way, as a symplectic or a pre-symplectic reduction. Okay, and just as in the other ones, these maps, there are several ways in which you can see its fibers of the Teichmüller space. Yeah, we have this fibers. So I think these are nice equations to study in the future. Okay, I think. So far, what we can say, at least, is what happens when alpha is very small. Bigger than what? Than the Teichmüller space? I mean, yes, yeah, you are right. It's fibers of a, if you like, you can reparameter things so it's fibers of the constant scalar Kerfachek Helix matrix moduli space, which fiber is itself of the Teichmüller. Is that what you mean? Yes. Yes. What he gets is what I just said. Yes, but what he gets is this. What I'm saying, it's fibers over the moduli space of constant scalar Kerfachek Helix matrix. That's fibers, you know, of the Teichmüller space. There is a torus action by, you know, symplectomorphisms modulo. Well, yeah, the ones, sorry, no, no, the connected component of the identity component of symplectomorphisms modulo Hamiltonian. I mean, it's a bit, you can do this. But finally, it fibers there. But yeah, if we had more time, I might explain it fibers of something in between too. But you are right. Good. Okay. So this, but I wanted to relate it to flat, modular flat connections, or universal modular flat connections. And this map is also there. But you're right. There are different ways of looking at different vibrations. I don't think so. This is new. This is new. And it depends on the parameter, okay, alpha. So I was saying that this symmetric tensor is not definite positive, sorry, positive indefinite. And so a priori, symplectic reduction doesn't give you a complex structure on the reduction. Still, we can work with some deformation theory infinitesimally and see that we get something for very small alpha. So in the weak coupling limit. So we fix a volume, the parameter epsilon, and a flat connection and a complex structure. And suppose that the flat connection is reducible. Okay? Suppose the genus is greater than or equal to 2. Then we get this. I mean, there exists an interval of the coupling constant for alpha not small, so that the orbits of this solution, I mean of this flat triple, if you like, contains an orbit for the, if you like, unitary extended case group of solutions of that equation. This is similar to Kempf's. Okay? And there is a neighbor. I mean, you look at this orbit as a point in this modular space I just said, and it has an open neighborhood for which actually the complex structure reduces. Okay? And so does the symmetric tensor, and they satisfy this too. And actually, the calculations also tell you that this quotient is finite dimensional by some ellipticity. I mean, the proof is kind of longer. Maybe I can say a little bit more. I mean, as I said, there is this vibration. If I add this more structure here, I could say more, but this composite is holomorphic. And we have the same properties of non-degeneracy and signature I said earlier for these induced symmetric tensor on the quotient. on U star, on this open neighborhood of our solution. Okay, so for -1, this is not generate, and define a pseudo Kähler structure, and epsilon equals 1, we don't really know. I mean, it could be degenerate. Okay, I mean, maybe I'm saying too much in this slide. This actually, you can write a Kähler potential by construction. Okay, just combining it with the Kähler potential for on the space of complex structures. And as I said, this is, I mean, when you do the deformation theory, you find that what you get is a multi-degree differential, coupled multi-degree differential operators, and this is an extension of the usual elliptic theory for differential operators, elliptic differential operators, and still you can work it, and it following this very useful paper by Lockhart and McGowan prove this theorem. Okay, now our last moduli space. No. The one before, the last one, is Higgs bundle.
This Nirenberg paper, it's a local kind of a result, right? It's an Rn.
Yes.
Is there a clean result applicable in setting of manifolds that you're quoting?
Yeah, it's there, but you're right that they don't. Yeah, you're right. I mean, the title of the paper says it's local, but we had discussions with these, not with them, but people who know about this, and this seems to be, Olivier Bicard in particular, and this seems to work in general.
I think there might be a more elementary argument. I mean, the problem
really?
is the scalar curvature, right? That's a fourth order term, and the others are second order. So you can write the scalar curvature, you can write a system of second order equations.
Yeah, we talk about this. Maybe. We have to talk about that. That's nice. Okay. Yeah, we discussed this in a different problem.
Yeah.
And maybe this applies here too. Okay. So now our third moduli is similar to the one for flat connections. In this case, we want the analog of the I complex structure in Nigel's paper. How do you construct it? This is the I. You look at this vibration X as the relative cotangent bundle of another vibration. Okay. And then you can prove that there is a J-dependent complex structure here, and canonical induces another one here, which is given by that formula. Okay. So we have a complex structure similar to the other main complex structure in the usual Higgs bundle theory. And we restrict to this space where the phi associated to psi and j, the 1-0 form, the Higgs field, if you like, is holomorphic. There should be an argument similar using Kähler vibrations, actually in this case complex symplectic vibrations, given this as a moment map, but we haven't yet proved this, okay? So we just impose it. I mean, the calculation involves calculating a minimal, a coupling form. Yes, sorry, this is del bar. Thank you. Okay. So what I'm saying is we have a complex structure I, and we impose some integrability condition that we actually hope has a complex moment map interpretation. There are still open questions, like that one. But still we can do it. So we do it. And what else do we need to make our constructions? We need, we have, yeah, that's it. From this point of view, we again use this identity component extended gauge group acting on this space. Okay, and we again propose that from this point of view, if we do the two-step construction of the quotient with respect to let's see. With respect to, should be some, in principle, hypothetical omega, something here. Even if not, we can do it. I mean, we can restrict here the Higgs bit and to construct this quotient, okay? This is, again, kind of a proposal, as in the first moduli. Later, we will have something more to say. But these fibers, again, of the Teichmüller space. Okay. So here is the proposal for the Higgs bundle moduli space is pairs of complex structures and unitary connections and these one forms for which the associated Higgs bundle is polystable, modulo this large, or in some sense complex, even though this is not any complexification of anything, but we can call it anyway, complex extended gauge group. Well, actually, the identity component of the identity component is extended gauge group. The right way of saying it. Okay. Now, our last moduli is kind of the Higgs analog of the harmonic bundle case. In this, I mean, it's defined by some equations. Okay. So we already have constructed some complex structure on X that depends on the, well, it's tautological, right? Kind of constant. And we also have we can use this other Kähler form, the one appearing in the simplex and in the construction of, I mean, the Hitchin's equations. Okay, this is the usual formula. But now we have a problem again, because this doesn't restrict, as we wanted, to this space of pairs given by, if you like, of or triples given by complex structure, a unitary connection, and a Higgs field. Okay. So what do? Is we add something. We construct a coupling form that restricts to this on the fibers. Okay, so we apply some machinery from the book by Wilhelm Lerman and Steinberg, and we managed to obtain a closed 1-1 form on the total space that restricts to the symplectic forms we wanted on the fibers. Okay, that preserves this space where the Higgs field is homomorphic. And it's given by this explicit formula. So it's, yeah, I should say what everything is. These VIs have a tangent vector to the complex structure space, and then one form tangent to the space of unitary connections, and then one form in the other direction of the complex connections. This is the formula now. Now it makes sense. Okay, but the point is, when these vanish, when you go in these other directions, you get. I mean, when J dot is 0, these 3 times vanish, and you get the original symplectic structure. So now as before, we can apply these weak coupling methods. Again, we have to fix a symplectic form to define the Kähler structure on the space of complex structures. Then we have constructed this coupling form, and we have this tautological complex structure. I said I. And this is a formula, as in the case of harmonic bundles, for the weak coupling, where there's again an epsilon, which could be plus or minus 1. And again, we have a similar behavior. For -1, the associated symmetric tensor is negative in the horizontal direction, and by construction, positive in the vertical direction. So this is non-degenerate. And in the case of +1, we have some signature changes along rays, lines. Okay. And this again gives us problems, as we will see. Anyway, we have this. We are repeating what we did for harmonic bundles. In this case, we now focus on this Hamiltonian extended cage group and its action on the space of X with this tautological complex structure and this minimally coupled Kähler vibration structure. And so the result in this case is that the action of the extended cage group, Hamiltonian extended cage group, is Hamiltonian. And the vanishing of the moment map is given by these equations. We call them coupled Hitchin equations, but in a sense, they are not coupled. You can solve for J here, and then solve for this, which are, in our notation, Hitchin equations. Okay. But I should say, it means I'm done or, okay. A little bit. Yeah, there's one slide. So I should say that if we don't impose this homomorphicity of phi, we get also moment map and the equations are more coupled, as in the harmonic case, harmonic bundled case. Maybe there is something extra there to understand. Maybe there is, yeah, another form to study. This may be related to the pre-quantum line bundle. I don't know. Okay. So we construct the moduli space, of the universal Hitchin moduli space appearing in the title, which is given by solutions of these coupled Hitchin equations, modulo the action of this Hamiltonian extended gauge group. And again, following Donaldson or just by composing maps, it maps its fibers over this Teichmüller space. So now we have the same problem as in the second moduli space of harmonic, the universal harmonic. What's the name of that? Universal moduli of coupled harmonic solutions of the coupled harmonic equations. And so still we can follow in these same techniques. In that case, we can prove a similar result. If we fix a volume, an epsilon, one of the two possibles, and a solution, sorry, a stable Higgs bundle, which means a solution to Hitchin's equations by Hitchin's, one of Hitchin's terms. But it has to be stable, not polystable. And suppose the genus is greater than or equal to 2, then for very small alpha, the orbit under this extended Hamiltonian extended, sorry, no, the big one, under this group contains an orbit of solutions for this other one. And if you look at that orbit as a point in the universal Hitchin moduli space, then it has an open neighborhood on which the complex structure descends. And again, we have the same identities. I mean, the symmetric tensor descends too, and we have the same identities. Okay, and as in the case, this map is holomorphic, and I mean, it's completely equal. The proof are very similar. And we have a pseudo, in the -1 case, we have a pseudo scalar structure on the moduli space, because it's non-degenerate in that case. So that's it. Thank you.
Yeah, so in your results about finding solutions for small alpha, I guess in principle, the alpha you take depends on the curve you're considering and the bundle you're considering.
Yeah.
Do you think that solvability of these equations, nevertheless, is actually independent of alpha for alpha very small, independent of the bundle in the curve?
I have no idea.
So if you imagine the analogous picture in variation of GIT, then you're doing GIT with respect to line bundles that eventually lie in the same chamber. So
yeah, I know, but I can't prove it. It would be nice.
And could I also ask about the assumption that the bundles are stable or the connections are reducible in your?
I mean, being stable implies they are simple. That's what we want.
But is the question interesting when the bundles are polystable, or?
I guess. Yeah, I mean, of course, because that would be the whole moduli.
Yeah.
We're only looking at them. an open subset that may be empty.
But that kind of question falls into the category of the things from the talks I was giving, like where you perturb from some polystable thing.
Yeah, they are interesting problems.
So you mentioned at the beginning you want to think of this as some kind of fields, all these different things, entities in your story. So I was wondering, is there a variational description of the equations?
Variation.
Variational description, an action principle.
I haven't thought about that. We had one for the original problem this started with, the one in Mario's thesis. But it wasn't really useful. So okay. Maybe, yeah, there should be maybe a kind of Mabuchi energy if that it's not the physical, what physics use, and well, principle, but maybe they do. But, well, actually they do now. But yeah, there is a Mabuchi energy we haven't constructed, but this should go through that part. And then that gives you a variational approach to those equations.
I see.
Using geodesics and, yeah, you know.
Thanks.
Does the construction of the universal moduli space work for
Which one?
punctured surfaces as well?
The construction of?
The construction of the universal. Does it work for punctured surfaces?
But I can't say. I mean, this already, I think, gives new conjectures that I would like to understand before, but that's quite interesting too. But yeah, but we are not there yet. I feel this is not going to be very in the near future, but this is a very interesting question. Thank you.